Okay, let's talk about Gibbs and his free energy. Who is Gibbs? I have no idea, but I'm assuming some scientist. And pretty much he comes up with this equation. Well, delta G is equal to delta H minus T delta S. Alongside of that, he creates two other equations that we'll discuss later. But this is the main one here. You might recognize delta H here. That's our enthalpy. Kind of like a heat of reaction, right? Where if it's exothermic, it's a negative value. And if it's endothermic, it's a positive value. We have here T. That's our temperature in Kelvin. Our last thing here is delta S. This is a new concept here. This is what we call entropy. You see how enthalpy and entropy pretty similar, so it's important to not get those two confused. What entropy is, though, that's our disorder. Pretty much, our universe always wants to be more and more disordered. What that typically means here is that we want to have less and less attraction to things around it. How that typically plays out in our case here is that a solid is going to have less entropy than a liquid, which will have less entropy than a gas. When we go in this direction, when we increase entropy, that's a positive. If we go the other way here and we start decreasing it, that's a negative. Okay, so let's now talk about another way we can find Gibbs free energy here. So let me scroll down a little bit here. The other way we can find it is if delta G is equal to negative RT natural log of K. And so again, delta G is our Gibbs free energy. R is our gas constant. You want to watch out for the units here. This gas constant should be in joules per mole Kelvin. T is going to be in temperature in Kelvin. And K is our equilibrium constant. We can also do this math with Q sometimes. So, can be Q. And we'll use this when we talk about equilibrium values. The last one we need to talk about here is that delta G is equal to negative NFE standard. N here, let me scroll down, is the number of mole electrons. We can think about it here as the number of electrons transferred. We have F. That's Faraday's constant. That's going to be 96,485, so 96,485 coulombs per mole of electron. And lastly, we have E here, which is our standard reduction potential. That's all three of the equations that we need to know here. This is all three of the equations here that we can use to figure out what delta G is. Okay, let's discuss what delta G actually means. So delta G can be negative, it can be positive, and that's what we really want to look at, when it's negative and positive. When it's zero, we don't really talk about that. But let's look at when it's negative here. So let's make a little chart here. Delta G. So when it's negative, we call that spontaneous. What does this mean? It just means that the reaction will happen. When it will happen? It doesn't tell us. It could happen in 1 second. It could happen in 45 years. It could happen in the next 4,565 days. We don't actually know. It just tells us if it's going to happen or not. A positive value then is going to be non-spontaneous, which means the reaction will not happen. We can also then extrapolate this using those equations above to kind of get a rough estimate of what conditions will cause spontaneity and which won't. Let's first look at delta G is equal to delta H minus T delta S. So again, let's make a little chart here. So let's take a look here. What happens if our delta H value is negative? Again, that means it's exothermic. Our T value, well, that's just a temperature. And again, temperature in Kelvin, so it's always going to be positive. Okay. Then let's look at our delta S value. Let's say it's positive. And again, that means that there's more disorder. Again, that means there's more disorder. That could be a solid going to a liquid, or liquid going to a gas, or it could be something where there's 1 mole of gas going to 2 moles of a gas. Well, what's going to happen to delta G then? Well, if you kind of want to do some pseudo math here, we're going to have a negative number here. We're going to be subtracting a positive number times a positive number. Well, we know here, if we were to rewrite it here, there was some negative value. That would be minus a plus. That just results in here minus a minus. So delta G then has to be a negative value, which means that it's spontaneous. Let's try another scenario here. Let's say that delta H is now positive. So that'll be an endothermic reaction. Again, T can never be negative, so it has to be positive. Let's keep delta S here a positive value. What's going to happen? Let's take a look here. We're going to have a positive value here, subtracted by, again, 2 positives multiplied by each other. We can say it's a positive value with another negative. What that means for us here is to determine if delta H is positive or negative. That's going to depend on our T value. So this one depends. So it's going to depend on our T value, our temperature. And again, because we want G to be negative, we're going to say here that entropy drives this reaction to be spontaneous. Okay, so we're going to say entropy drives reaction. Because again, what's causing delta G to be negative? It's not the energy released by the reaction. It's by the reaction making more disorder. So again, this one is going to depend on our temperature value. So let's look at when delta H is still positive. And let's say the delta S is now negative. Again, we can do the same math here. Let me erase the one up top. Same type of math here. So this is going to be a plus minus plus times a negative now. So we actually result in here a positive, some positive value, minus a negative value. Well, that's a positive plus a positive. Well, that means that delta G value is always positive then. And this is going to be our non-spontaneous condition. Finally here, let's say delta H is negative and so is delta S. So again, let's do the math here. we say this is a negative minus positive times a negative. Well, guess what? That's going to result in a negative minus a negative, which is going to result in a negative and a positive number. That means that, again, this is going to depend. It's going to depend on the value of temperature. In this case, typically the lower the temperature, the more likely it is for the reaction to be spontaneous. And so in this case here, we're going to say that enthalpy is going to drive our reaction. Because again, it's our energy released here that's making it possible to do this reaction. So those are all the possible things here that this chart could be. Only ones that we know without doing any math is going to be when we have a negative enthalpy and a positive entropy, or when there's a positive enthalpy and a negative entropy. The rest of them, though, we have to do the math to determine if it's going to be positive or negative. Let's look at the next equation. Delta G is equal to negative RT natural log K. This one's a little bit more simpler here. So again, let's move up the chart. R and T are essentially constants. We can think about them as constants. R is our gas law, its same value. We want to make sure that it's the one in joules divided by moles Kelvin. But essentially, it's going to be 8.3 around there. T is always temperature in Kelvin. It can never be negative. So essentially, here we have a positive and a positive value. So as long as that K value is greater than 1, delta G will be negative. And if you want, you can go do the math on this. Don't plug in 1, but plug in something else here. Maybe plug in 1.5 or a 2 or something like that. And we'll see it's negative. We can also say that, hey, well, we know that K, well, that's our equilibrium constant, right? And if K is greater than 1, that means our product's favored. Well, that's going to mean then we want to do our reaction, that a reaction happens. So again, that's how we can think about that as well. A reaction needs to happen. Delta G is spontaneity, or if it will happen. Well, if we know from K that it will happen and goes to completion, then we know that our G value should also be negative. We can try the same thing here with saying K is less than 1. And again, that means that we're the reactant favored. And if you want to think about it like that, okay, well, if we're reactant favored, are we actually doing the reaction? No, right? Typically, we're not reacting at all. Or if we are doing in a very small scale. So again, if you want to think about it like that, then it makes sense that delta G is positive. It's not that favorable to the reaction. It probably won't happen. Let's move on to the last reaction here. Delta G is equal to NFE. I just got the negative there. Whoops. So let's break this down here. N is always going to be a constant. It's the number of moles of electron. Right? Number of a mole of electron. That's always going to be a positive number. We can't have negative electrons transferred. This will always be positive. Faraday's constant, like I said above, that's always positive. So as long as E cell is positive, we're going to have here a negative delta G value, right? We're going to have 3 positives multiplied by each other, and we have a negative on the outside. So this will always result in a negative number. We haven't talked about what E is yet. We said it was a standard reduction potential. When we talk about cells, though, our electrochemistry, this is going to be the cathode minus anode values. And again, what this tells us here, if it's positive, our cell is working. And if it's negative, it's not working. So then if E cell is negative, it's not working. It would make sense for delta G to be positive. If it's not working, the reaction not taking place. We're not changing, we're not transferring those electrons. So again, we're not doing the reaction. That's going to be all for today. If you guys like the video, subscribe and leave a comment and tell me what you would like to see next.